So today I'm going to present our work on low resource learning on graphs. Right. So I think probably many of you here already know what graphs are. So graphs can represent complex big data. So not just the entities, but also the all kinds of relationships between the entities. Right. So it can be it's quite widespread in different domains, like in social networks, in biology, in e-commerce, or in knowledge graphs. Right, so here is a overview of this talk. So I'm going to, so the talk revolves around our data on graphs or networks, all right? So among the graphs, there can be so-called heterogeneous graphs, right? So in heterogeneous graphs, there can be some specialized graphs like user interaction graphs, which is typically used in recommendation, or knowledge graphs. And the problem we are tackling here is low resource graph representation learning, right? So there are two kinds of scenarios. One is structure scarcity, the other is label scarcity. So I will get a bit more into this later. So, and to solve this problem, we have a suite of tools to solve this. So such as meta-learning, pre-training, or augmenting with external knowledge. Right, so of course, all these work are not possible without my co-authors and collaborators. So let's get a bit into the low resource problem on graphs. So the first kind of problem is basically similar to low resource learning in other domains. So it's a label scarcity, right? So we don't have enough label data. So let's take this graph as an example. So we have, let me see my pointer here. Okay. So so in this is a paper citation network. So all the nodes are papers, right? So some papers belong to traditional topics like SVM or neural networks. So for these kind of nodes, we have enough labels, right? But we can also have emergent topics like explainable AI or fair machine learning, right? For these kind of topics, because it's an emergent topic, so the label is we don't really have enough labels, right? And the quality of the label could also be not sufficient. So this is the label scarcity problem. So where we have novel classes, emergent classes, and we don't have enough labeled data. And another problem that's unique on graph is the so-called structure scarcity, right? Because the main difference between graph data and other kind of data is that we have relations, right? So some nodes have many connections to other nodes, but some nodes only have very few connections. So if you look at this diagram here as a node rank by degree, right? This is a typical node degree distribution in many networks, right? So only a small percentage of nodes have really high degrees, but most of the nodes in the table here, they have only maybe 1 or 2 links, right? And if we look at the classification performance with respect to node degree, right? So this diagram here is we divide the nodes into different degrees based on their degree. And those nodes with higher degree typically has better performance because they have a lot of links to leverage. But those nodes with these very few degrees, like the first group here, the performance is actually quite worse. There's a big gap between the performance of other groups. But unfortunately, for most nodes on the graph here, they actually belong to the group with least degree. Okay, so how do we solve this low resource problem? There are a few different learning paradigms that we can rely on. Right, so let's talk about the most traditional supervised learning setting. Right, in supervised learning setting, you have a set of training examples, and you have some test examples that you want to make predictions on. So based on the training examples, you basically learn a classifier, right? So you learn the parameters. The parameter is basically a classifier that can map an input instance like image here to a label, right? But the problem with supervised learning is that to perform well, you need many labeled data. And it's often hard to deal with novel classes. That means you can only classify the classes you have seen in your training data. If you have a new class, you cannot deal with it. But how does human learn? So even for toddlers, if you just give the child one or two examples, like in this picture here, only one example of a toy whale, he can easily distinguish what is a whale and what is not, right? He can learn just from one or two examples, and that's amazing. But how does the child actually do that, right? It's not just because he learn everything based on the given example, because he has some prior knowledge, right? So in his growing experience, he has came into contact with some other sea animals, all right? Not necessarily a whale, but he may have seen other sea mammals, and he have an understanding of how animals looks like and how non-animal like other transportation vehicles looks like, right? So based on this prior knowledge and with this additional example, he can quickly adapt his prior knowledge to make a correct classification, right? So we can actually get inspired from how humans learn and use a so-called a different paradigm from supervised learning, which is called meta-learning, right? So there are different lines of meta-learning, but here we're just going to focus on this particular work called MAMO. So in this work, in the training data, it's no longer individual instances, right? Instead, each training instance is a task, right? So you can see this, each box here is one training instance. And in this instance, we call it a training task. It has a support set and a query set. And the support set is like a mini training set within this task. And the query set is like a mini testing set, all right? So given these training tasks, we don't learn a classifier directly, right? Instead, we learn a prior. So this file here is a prior that we learned from the training task. And at testing time, each testing task also contains a support and a query, all right? The support is basically one or few examples for each novel classes. So you notice here in the test class, this car and ship, these two classes does not actually appear in the training set, but you give it one or two examples for each class, and that's called the support set in the test data. So by leveraging the prior and doing an adaptation on the support set in the testing task, we can finally get a classifier. And then we use this classifier to map an image to a car or to a ship, right? So the key idea here is that in the training stage, we do not directly learn a classifier, but we learn a prior that can help us to adapt to testing tasks in future to deal with novel classes. So this is called learn to learn, because we do not actually learn a classification function, but we learn a prior that allow us to learn a classifier. So this is why it's also called meta-learning, right? So, but the problem with meta-learning is that it still requires many labels on these base classes, right? So you notice in this meta-learning, we need a lot of training tasks. Each instance is actually a task, and we need a lot of label data on these training tasks, right? But what if we don't have such base classes, right? Let's say I only have one or two examples for the classes I have here, but I don't have those labels on the base class. So an alternative way is to rely on self-supervised learning, right? So most of the self-supervised learning can be can fall into one of the two categories, either generative or contrastive, but of course there are some that's a combination of both. So in generative, one typical approach is typical encoder-decoder architecture, all right? So we try to minimize the reconstruction error, right? Given an input image, we do some encoding and then decode. We get a reconstructed image and we try to minimize the reconstruction error between them. And another way is contrastive, all right? So basically we generate some samples. Some of them are considered positive samples, some are negative. Like in this example, the first pair is considered a positive example because these two are the same cat, right? It's just a different view, a rotated view. The second example here is two different cats, so they are labeled as different, all right? So the good thing about this self-supervised learning is that we get free supervision, all right? We do not need any additional annotation cost. So using this so-called label-free data, so these we still have these images, like the meta-learning, we have those images from the base classes, but we don't need to have labels on them, right? The images are very relatively cheap to obtain. The difficult thing is getting label. So we can use this a large amount of label-free data coupled with self-supervised tasks. We can do some pre-training, all right? So given the pre-trained model, we can use it to initialize different downstream tasks, right? So let's say we have a task 1 is on some image segmentation, maybe task 2 is on some object detection, right? For different tasks, we do different fine-tuning, right? Fine-tuning would require some task-specific labels. But compared to traditional supervised learning, the amount of labels required is much less because we already did some pre-training. We only need some fine-tuning to make the model adapt to each task. Right? So this is about pre-training. Then another complementary method is try to augmenting with external knowledge. Right? So like this example here, we are doing some object detection. So let's look at the bottom example here. So this one, the one on the left, it's a regular model, doesn't use any external knowledge, right? So probably it can only detect a person here, right? So this blue label, a person is detected, but fails to detect a surfboard. Because from a picture, the surfboard maybe only have a few pixels visible. So it's really difficult for any algorithm to pick that up. However, if we bring in external knowledge, we know that a person standing on a sea is actually usually standing on a surfboard, right? So with this knowledge, we can actually push up the detection of a surfboard, right? Another common thing is in recommendation, all right? So in typical recommendation, we only have user interactions, right? Which user bought which items, right? Or watched which movies in this case. But we can also brought in a knowledge graph here, right? So we can connect these movies to their actors and their directors, right? And potentially these actors and directors, they also have other relationships between them. So with this additional help from the knowledge graph, we can also improve the performance. Suppose we cannot increase the amount of label we have, then we can use additional knowledge to push up the performance. Right? So I think that's a introduction of the problem and the overview of the methodology. So I think in the next, I'm going to go into a bit more details in learning on graphs, right? So the previous examples, we used some examples from like computer vision and other domains, but now we are going to see how we can actually use those methods for graph data. Right, so the first one is I'm going to introduce this structure scarce learning, all right? So as I mentioned earlier, there's a lot of nodes in the graph with very few links, right? So these are very a common scenario. So in a social platform or in a recommendation system, these nodes could be a new user, right? They just join the platform. They don't have a lot of interactions. Or it could be existing users, but they are less active, right? So this contributed to the very long tail here with very few degree. So the thing with this distribution is that the tail nodes, the nodes in the tail, they have very low degree. They are not sufficiently modeled, right? So there's a bias towards those nodes with a large degree, right? So the reason is because these tail nodes, they don't have structural information, right? But existing methods, whether you are using network embedding or graph neural networks, they all regard all nodes uniformly. They do not pay special attention to the so-called tail nodes. And this results in a worse performance for the tail nodes, right? So our problem statement here is that suppose I have the embedding vectors of the nodes learned from a base embedding model. It can be any base embedding model. It can be a graph neural network or a network embedding. Can we actually refine or improve the embeddings of the tail nodes, right? How to make the tail nodes to push up their performance to be maybe still not as good as the head nodes, the nodes with a large degree, but try to make them better. So the assumption here is that head nodes have high quality embeddings, right? So based on this assumption, we use a few insights, all right? So we try to predict high quality embeddings by looking at the head nodes, right? Try to see how the head nodes can generate high quality embeddings, right? So we use the head node to simulate a mini regression task. And then we need to do some simulation because head nodes are different from tail nodes, right? Head nodes has a lot of neighbors. So we need to perform link dropouts on head nodes to simulate the tail nodes. And then we also need to consider the special situation on graph. On graph, there is a locality problem, all right? Different nodes on the graph, they reside in different local contexts. Their neighbors are different. So if you just do random sampling for the support set, it's going to be not working as well. We have to consider the topology on the graph. So we use a meta-learning to do this because meta-learning can actually help us to realize our insights, right? So first thing is each head node like V here, it has a lot of neighbors, can be a meta-learning task, right? So we do some link dropouts here to remove some of the link to simulate it as a tail node. Then in this task, we have some support set. So in a typical meta-learning scenario, the support set is typically randomly sampled. But here we are going to sample from the head node's neighbors, right? Because of the topological structures, right? Neighbors on the graph, they are assumed to have some similar behavior. And we try to learn from the support set, right? It's a regression problem to see how we can map from each support node to their embedding vector. Then we try to apply the model, the learned regression model on the query set, the query data. The query data is the head node, and try to see how we can recover the supposedly higher quality embeddings of the head node, right? So basically, in the training stage, in the meta training stage, the tasks are constructed from the head nodes, right? So we can learn a prior. So the prior is learned by adapting to the support set. And then we optimize the query loss and backpropagate to the prior. So in the testing stage, we look at the tail nodes, right? So the tail nodes also has a support set. We try to see how to use the support set using the learned prior to predict on the actual query node, which is to give us the embedding of the tail node, all right? So by using this meta-learning framework, we actually enable a kind of knowledge transfer from the head nodes to tail nodes. So the main high-level idea here is that we look at how head nodes is able to generate their high quality embeddings and transfer that common knowledge, the prior, to the testing stage, right? for the tail nodes. So here are some visualizations of the embeddings we learned, right? So diagram figure A here is a base embedding method, right? It can be any method, right? So if you look at this diagram here, the solid points are the tail nodes and the hollow points are the head nodes. So you can see that the head nodes actually are quite well classified, right? So they are in separate clusters. But if you look at the solid nodes, all of them are in the middle. They are basically not very well separated, right? This is because for tail nodes, we don't have enough structural information to learn a good representation. But after refining by our method, you can see that the solid nodes also move away, right? Move to their respective clusters. So the solid points, the tail nodes, no longer they are in their respective clusters, right? So this shows that our method can actually improve the embedding of the nodes. But there are still some limitations here. So the meta-tail to back model is the two-stage approach, right? In stage 1, we use any base model to generate node embeddings. And in stage 2, we refine the tail node embeddings by meta-learning. So is there a way to make it end-to-end, right? Because if by using a two-stage approach, then in stage 2, you are only doing a corrective action, right? If there are some fundamental issues in the base model, typically it's too late to correct it. So an end-to-end approach might be better, right? So due to time constraint, I'm not going to details of the end-to-end approach, but basically it follows a similar script, right? It tries to transfer knowledge from head nodes to tail nodes, right? It also performs link dropout on head nodes to simulate the tail nodes, and then learn a global prior. The global prior can be adapted to the individual nodes, right? Using also a meta-learning mechanism, but actually using a different meta-learning mechanism. But the high-level idea is similar to the approach. But by using a different meta-learning mechanism, we actually able to make it end-to-end, right? So so the key idea here is that common knowledge and then enable the transfer of knowledge to them to so these two work are the how to refine tail node, right? One application of this is actually in cold start recommendation, right? So in traditional recommendation, for collaborative filtering, we are looking at this user item interaction graph, right? We have users and items. But in cold start recommendation, we focus on the new users and new items. So basically, the new user here have very few connections, right? So basically, it's also an instance of structure scarce learning, right? It's actually a tail node. So to solve this, we actually apply two ideas. One is how to enhance it at the data level, right? So a traditional way is to consider content, right? Traditional content-based augmentation. Consider the attributes of the user. Another way is to use the knowledge graph, because the items could be have a hierarchy, right? And the item could also link to other entities, right? So in this case, if we are doing movie recommendation, the knowledge graph would be directors and actors that interconnects all the different movies. So this is the data level augmentation. At the same time, we can use meta-learning, right? Because here it's basically the same as what we see before. The cold start users table nodes, right? How we can learn a global prior from the meta-training users. In the meta-training user, we use those users that have a lot of interactions, right? We try to learn a prior, and this prior can be adapted to a new So basically, there are two ideas here. So bring in additional knowledge from the knowledge graph, we try to construct meta-training tasks with so-called semantic context, right? So in a traditional meta-learning task, the support set are just the nodes, but here we also bring in additional semantic context based on knowledge graph, right? Because the knowledge graph allow us to reach to other related movies, right? Which is not possible without semantic enhancement, right? Another thing is when doing an adaptation from trying to adapt the global prior to the tasks, the support set for the tasks, need to perform a co-adaptation, right? Both at the semantic level and at the task level. So if we look at this result, I think it's very interesting to look at this. So we have 4 different scenarios in code start recommendation. One is this UIC is both user and item actually code start. UC is only user, IC is only item, and then we also have a non-code start scenario. So if you look at our performance gain here, so this figure here is the performance gain with respect to a non-code start approach, right? So you can see that the more code start we have, actually we have higher performance, right? And YC is both user and terminal performance improvement. This is because for this scenario is the most difficult. For non-code start approaches, they really perform very bad in this scenario. And another thing is you can look at the impact size of the support set. Right? So basically, support set is in each task there is a kind of a mini training set for the task. Each task here is a user, right? So if we reduce the support set, you can see that some competing methods, their performance actually degrade severe, right? So this is MAE, so the higher is worse, right? But for our method, we're actually quite robust. Even if you reduce the support set, that means the number of examples in the becoming smaller and smaller, we are still quite robust, right? Don't decrease so fast. This is because we let the code prior and can adapt it to the post-start users. Right? I think that wraps up the structural start learning on graphs. So there's the last part is on label start learning on graphs. So let's start with this classic paradigm for learning with insufficient label data. This is semi-supervised learning. So basically in semi-supervised learning, we have some label data, but we use unlabeled data to supplement it, right? Basically, we exploit the intrinsic structures between labeled and unlabeled data. And in traditional semi-supervised learning on graphs, okay, so those methods like label propagation, they are a transductive setting. That means you only learn on each graph, right? Your learned model cannot be applied to other models, right? So each graph is on its own. On graph 1, you learn a model applied to the test data. On graph 2, you learn the model. It's the transductive approach. Then we have the inductive approach. Most modern graph neural networks can do inductive approach, all right? Basically, they have a set of training tasks, a set of training graphs, right? From these training graphs, they learn a graph neural network model, right? The model weights can be applied to testing graphs, right? So the benefit of this compared to transductive is that you are able to leverage more training data, right? Not just restricted to one graph, but you can have a set of training graphs. But the problem is that here is one model fits all scenario, right? We just learn one model based on all these training graphs and try to make it inductive to all the testing graphs. So this ignores the differences between the graphs or the differences on the graph. So instead, we can also use meta-learning to solve this. So we call it meta-inductive cross-graph GNNs, right? So given a set of training graphs, given a prior, and this prior can be adapted in 2 levels. So first, in the first level, it can be adapted to different testing graphs, right? Because each graph is different. So if you just use a common prior on all of them, it's going to be some of the fine differences between the graphs. So we do the first level graph, first level adaptation, adapting to different testing graphs. And then on each testing graph, the tasks can be different, right? On one graph, you may involve class 1, 2, 3. On one graph, you may involve class 4, 5, 6. So that essentially, there can be different classes, different tasks. So we do another task level adaptation, right? So by doing this dual adaptation, we are able to adapt to and take care of the differences between different graphs and different tasks. So this is a major difference between from traditional inductive approach, where in traditional inductive approach, you learn a fixed model, and this model is applied to all of the future instances. But here we are actually going to adapt the model, adjust the model to suit different graphs. Right? So we can look at some performance heat maps here. So these heat maps, the horizontal axis are different settings, right? We have transductive setting, inductive setting, and our meta-inductive setting. The y-axis, we have 3 groups, which is the similarity between the training graph and testing graph, right? You can have high similarity, medium, or low. So for transductive setting, you can see that basically there is no change in different groups, right? Because transductive only learns from this one single graph, right? So there is really no training and testing concept. So it doesn't require a training on separate graph, so there is no change. But for the inductive setting, as you can see that for inductive setting, if the testing graph is very similar to the training graph, then it can have good performance, right? But if the testing graph is different from the training graph, then you see a noticeable performance drop here, right? So F1 score is actually a more severe drop. That's natural, right? Because the testing graph actually have a different distribution from your training graph. But using our adaptive meta-inductive setting, right? We don't just apply the inductive model on all the testing graphs, but we do some adjustment, right? By doing this adjustment, we can see that our performance drop is actually quite small, right? Of course, there is still some performance drop if your testing graph is quite different from the training graph, but the drop is minimal compared to the traditional inductive setting, right? So this shows that the importance of adapting different graphs for different tasks. So that's for semi-supervised learning. And I think more recently there's this paradigm called few-shot learning. Right? Basically, in few-shot learning, only have a few examples for each class. So one way is we have some base classes. And in this graph here, we have these traditional topics, papers from traditional topics like from SVM or from neural networks. They have a lot of sufficient labels, right? But for emergent topics, like what we call novel classes here, explainable AI or fair machine learning, because they are emergent, so there are very few labels for each class. So we can use meta training here, meta learning here, right? So basically, we do the same thing. In each training task, we have support and query. We then, from the support, try to adapt the query, right? And the prior learned can be transferred to the method test tasks to handle the novel classes. But there's a problem here, right? In graph, the support and query nodes, they have dependencies. It's unlike in computer vision, each image, they are just randomly sampled. But in graph, if we use random sampling of support and query, some nodes could be pretty far away from the graph. How do we capture the dependency in the nodes? How do we leverage the topology information in the graph, right? So basically, we use the actual hub nodes, right? So hub nodes help us to locate or to reach nodes within each task. The support and query nodes can be very far away in a task, but by bringing them to the hub nodes, we can actually model their dependency, right? But at the same time, the hub nodes also help us to pinpoint to the location on the graph, right? Because the hub nodes are generally structurally important nodes on the graph, right? So we can map each task to a graph level, to achieve a graph level, right? So by considering both this within task dependency and the global dependency, we can actually do a few-shot learning on graphs using the method, right? So, but as I actually mentioned earlier, there's limitations of meta-learning. We need enough base class labels to construct meta-training tasks. So what if we don't have sufficient labels for meta-training? Okay, so one common way is using pre-training, right? So we have here, we use some self-supervised task on label-free data to do some pre-training, and then the pre-trained model can be fine-tuned to So there are generative and contrastive methods, right? So earlier I talked about this in the image context, but on graph you can also have generative methods. So the generative methods basically looking at how we can generate the attributes, node attributes, or edges between nodes, right? So to maximize the likelihood of those observed edges. Or contrastive, we can construct different views of the same node. Like these two networks here. The first here is the different Eagle networks sampled from the same Eagle. Right? Then those from the same node can be considered as a positive example, but those from different nodes, the different Eagle networks of random nodes can be regarded as negative samples. Of course, we can also extend them to heterogeneous graphs where we have different kinds of node types and node relations, right? So I think due to time constraint, I'm not going into the details of the heterogeneous graph, but the basic idea is, apart from the capturing the structural information on the graph, we also try to capture the semantic information on the graph. So we can capture the relation level or subgraph level semantic nodes, or we can use network schema. Right? So in a heterogeneous graph, the network schema is actually reveal a lot of information about the overall relationship between nodes. So by leveraging the schema level semantics, we can also define some training tasks in graphs. Right? But there's a problem with this retraining approach. Is the divergence between the pre-training objective and downstream objective, right? So we can see that in pre-training, we are doing some like edge generation or attribute generation, or maybe some other contrastive process. But in the downstream, we are actually doing like node classification, graph classification, or maybe detection, right? Before graph tasks. There is a gap between the pre-training objective and the downstream objective. So how do we actually close this gap? Another issue is for the fine-tuning step, right? When you have the pre-trained model, you need to do a fine-tuning. But the fine-tuning can be expensive for large models, right? And it may also easily overfit if there are very few labels from downstream. So one way is to consider the fine-tuning step within. So in this work, we are actually doing a simulation within. So in pre-training step, we also design some simulation tasks, assuming it's our task, and do some simulation to make sure whatever you can do adapted to the task. But I think the problem is that it's not a fundamental solution because we are using a simulated task. Right? Simulated task is still not the actual task. Right? So it's not a fundamental solution. An alternative way is to use the prompt. Right? So it's originally proposed in NLP. It's basically an instruction to reformulate your original task to unify with the pre-trained model. Right. So let's see this example here. So I missed the class today, right? So if I ask you to do a sentiment classification, if you use a traditional model to do it, probably you will say it's a kind of maybe neutral because there isn't strong sentiment in this sentence. Also, most of the words are quite neutral. Right? But if you use a prompt is basically a natural language instruction, right? To try to query the pre-trained model. So the prompt here says, I felt so blank. Then you ask the pre-trained model to fill in the blank. Right? If your pre-trained model is doing a good job, then it probably will fill in the word like unlucky here, right? And with the word unlucky, it can be easily mapped to the negative sentiment, right? So essentially here the prompt is a reformulation of the original task, right? Reformulating sentiment classification into filling the blanks, which is actually the same objective as if you are using mass language model, you are actually already doing so, right? So this prompt here can be either handcrafted, right? From prompt engineering, you need to engineer the right prompt to get the right answer, right? So it can be used in zero-shot scenario. Or it can be few shot. In few shot scenario, you can use learnable word vectors. Essentially, each word token is eventually mapped to some vectors, right? So if we can learn the vectors automatically using few shot data, and that's better than handcraft, right? So this is called prompt tuning. So in graphs, seems that we can leverage the same idea, prompting to define the different tasks, right, with the pre-training task. So there are two challenges. How do we define various pre-training graphs? How do we design prompts on graphs? So by the way, this paper is just accepted by WWW, so it hasn't been officially published, right? So basically, we are trying to draw insights from NLP. We try to design a unified task template based on subgraph similarity recognition. And then we design a learnable prompt to guide. For the unified task template, we can map different tasks into the same template. Like for link prediction here, we can use similarity of the two subgraphs containing nodes, right? If they have a high similarity, then probably there is a link between them. If there is a low similarity, then probably there is no link between them. For node classification, we can also map it to similarity computation of subgraphs, right? Basically, we look at the nodes subgraph and the class prototype subgraph. So the class prototype subgraph is basically constructed from the given label data, right? From labels given, we can actually construct the class prototype. Then we compute the similarity between the nodes subgraph and the prototype subgraph. So whichever has the highest similarity with the guide us to classify into that class. And then the same thing for graph classification, right? You can use similarity between the graphs of different instances. So basically, by doing this, we converted all the major tasks on graphs to subgraph similarity computation, right? So the pre-training and the if we pre-train with link prediction, the link prediction is a good task for pre-training because links are already there. We do not need additional label data. Then we can easily apply to the downstream tasks, which are also in the same template. Then how do we design our prompt? Because different downstream tasks, they require different graph readout. Because we are computing the similarity between subgraphs, we need the graph readout operation to aggregate the node representation to graph representation. And different tasks may require different readout, right? Some tasks, maybe they are focusing on the particular features for certain classes, right? In other tasks, maybe it's another set of features that's important. So we need to use different prompts to guide them for whichever task, which part is more important, right? So basically, we are using I use either a prompt vector or prompt matrix in the readout. So when aggregating the node embeddings, get the graph level representation, you can multiply with let's say a prompt vector or a linear transformation, right? So it's not you don't have to follow a particular way, but these are just different alternatives. But in practice, we find out that using a prompt vector is really better because the prompt vector has fewer parameters than a matrix. And so downstream task only has very few labels, the smaller model size is going to be better. Right? So I think here are just some notes. So I think I want to show you this one. That this is our model downstream model parameters compared to other models. Right? Our GraphPrompt method, we only need to update 96 parameters, right? But for traditional supervised model or other baselines, they have much larger model size. So this is a comparison on the parameter efficiency. And parameter efficiency is important because the updating time is going to be much cheaper, and also you can deal with few short scenarios much better, right? When you have few labeled examples, the smaller the model, the better. It's less likely to overfit. Right? I think these are some